So next we have number 16, where this time we have to solve an initial value problem. So we no longer have just a differential equation, but there is a supplementary condition as well. And recall that this is an initial condition because only one value of the independent variable x is involved, pi divided by 12. And you can see what the equation is: 8 cos squared y dx plus cosecant squared x dy equal to 0. So we start the solution as usual. The given differential equation reduces to this form, which we obtain by multiplying both sides by secant square y times sin square x. And in this form the variables have been separated. To facilitate integration, we do a little trigonometry here. In place of 2 sin squared x, we write 1 minus cos 2x. So you are left with 4 here and the rest is same. So now we can integrate both sides. So integrating both sides, we get, of course, this integral of 4 times 1 minus cos 2x with respect to x plus integral of secant square y with respect to y, that equals c, where c is an arbitrary constant. Now what are these integrals? Integrating 1 with respect to x, you get x. So that's how you have 4x. Integrating cos 2x with respect to x will give you sin 2x divided by 2. The minus sign will remain. Because you have 2 in the denominator, after cancellation with 4, you will be left with 2. So minus 2 sin 2x plus integral of secant square y with respect to y is tan y. So that equals this constant. So you have now got a one parameter family of solutions for the differential equation. But now we will use the initial condition to find the value of c. And the initial condition is this: y of pi over 12 equals pi over 4. Now if you substitute pi over 12 for x, here we will have pi divided by 3 because 4 is multiplied. And here 2 times pi over 12 is pi over 6. So minus 2 sin pi over 6 plus tan of pi over 4, because y is pi over 4. The value of pi is pi over 4 when x has the value pi divided by 12. That is equal to c. Now what is sin of pi divided by 6? 1 divided by 2. Multiply that with 2 and here you are getting minus 1. And tan pi divided by 4 is 1. So after cancelling this minus 1 and 1, you have c equal to pi divided by 3. And you use that back here, and that gives you the solution of the IVP. This equals pi divided by 3. Next, let us look at this number 21. It's an odd numbered exercise, so we are not going to solve it, but we will use it to solve the next one, 22. It has 2 parts. This is part A. These things are left to you. It's extremely easy. We have to show that this following homogeneous equation is exact if and only if b is equal to c, and the equation is ax plus by times dx plus cx plus dy times dy equal to 0. And next let's see part b. And in part b we have this other homogeneous equation which is exact if and only if b is equal to 2d. Here we have b and here we have d, and e is equal to 2c. Here we have e and here we have c. And you can see the equation: ax squared plus bxy plus cy squared times dx plus dx squared plus exy plus fy squared times dy equals 0. And now we are going to use this exercise to solve number 22. And this is number 22. Solve each of the following by 2 methods. One method comes from this previous exercise and the other one is, it comes from the fact that these equations are homogeneous. So we are going to solve only part A and part B is left to you. You can see, we do not have it here anymore, but that other homogeneous equation, ax plus by times dx plus cx plus dy times dy equals 0, that is exact if and only if b is equal to c. If you compare that equation with this one, here A is 1, B is 2, C is 2, D is minus 1. So B and C are equal. So that is why by this exercise this is exact. We know that it's exact, and that's how then we go for solving the equation using the method for solving exact equations. That is one method, and then we will also solve it as a homogeneous equation. That is the other method. So we start the solution, and again I am saying that we are only solving part A here. This is left to you. We start the solution like this. Because this is equal to this, so by exercise 21A part A, this equation is exact. Alright, and now you recall the method for solving exact equation. Equations which are of the form m dx plus n dy equal to 0. So accordingly we also name these two functions. Let m be x plus 2y and n be 2x minus y. So knowing that this equation is exact, now we know that there exists a function f which satisfies these two conditions. The partial derivative of f with respect to x is m, and the partial derivative with respect to y is n. And we are now going to seek such a function f. Now we have to determine f, and you already know how to do that. You are going to integrate both sides of this first equation partially with respect to x, obtaining some information about f, and then we are going to use this one also. So without writing everything in detail, you just do what I said just now. You integrate the first equation partially with respect to x. You can write those things here. I have just simply written we have. So the left hand side would become f. Integrating x with respect to x, you get x square divided by 2. Integrating, okay, not differentiating. Do not write 1 here. Y is constant when you are integrating with respect to x. So this term becomes 2xy plus phi of y, where phi is an arbitrary function. I should have written arbitrary, but you understand, you write these things, okay. Phi is an arbitrary function of y only. Why do we need this part? That is because now if you go back by differentiating both sides partially with respect to x, this will vanish. That is why this can be any function of y. So next we use this equation 2x minus y equals del f del y, but in place of this now we use this expression for f and differentiate this partially with respect to y. This term will contribute 0, this will become 2x, and here ordinary differentiation will come because you are differentiating partially with respect to y, and here you only have y. So it turns into ordinary derivative of phi prime of y. So you can now see that you can cancel 2x and 2x from both sides. So after doing that cancellation, this is what you get, phi prime of y equals minus y. And then you can integrate both sides because only the variable y is involved in this equation, and it's an ordinary differential equation. Solving it, that is by integrating it with respect to y, this is what you get, phi of y equals minus y squared divided by 2. And you know why I am not writing a plus arbitrary constant here. That is because when we write the solution to the final equation, there you already will have an arbitrary constant. If you write another one here, that can simply be merged with that one. So there is no need to write that here. So this is one of the possible phi's, and using this phi back here, you get f completely as this expression, which itself is a function of x and y both, x square divided by 2 plus 2xy, which were present earlier, and now you know that in place of phi you can take this one, minus y square divided by 2. Is this the solution? No, this is not the solution. The solution is a slightly different equation. The solution is this, and we write this last part somewhat formally. Hence, a one parameter family of solutions of the original differential equation is f equal to constant. or this thing equal to C, where C is an arbitrary constant or parameter of this family. So this is one of the methods. Now we have to again solve that same equation using the observation that it's also a homogeneous equation. So we start again. This time, first of all, the differential equation, the original one, is given in differential form. We turn it into derivative form, and in this form it looks like this: dy dx equals x plus 2y divided by y minus 2x. Dividing the numerator and denominator by x, you turn this ratio, this function, into a form where the entire thing becomes a function of y divided by x, and that is why the differential equation is homogeneous. So now we can apply the theory of homogeneous equations, that is, you will now bring in that transformation y equals vx and you do the usual stuff. And that transformation, of course, is this y equals vx. We will now get rid of the variable y. Instead, we now have a new variable v to replace it. If y equals vx, differentiating both sides with respect to x, you get dy dx equal to v plus x times dv dx. You apply the product rule for differentiation. And you use this here to turn this equation into another differential equation where y is replaced with the variable v. In place of dy dx, you write this v plus x times dv dx. That equals 1 plus 2 times v. Y divided by x is v, divided by v minus 2. Now, it turns out from the theory that whenever we apply this transformation, we get an equation that is a separable equation. So we next manipulate this equation a little. We bring v over to this side. So it becomes minus v, and on that side we are left with x times dv dx. And if you do the calculation here, this is what you get: 1 plus 4v minus v square divided by v minus 2. Now this is a separable equation, and separating the variables, this is what you get: v minus 2 times dv divided by 1 plus 4v minus v square equals dx divided by x. So now we can do our usual integration. So integrating both sides, this is what we get. On the left hand side, we did a little trick. We multiplied and divided by minus 2, so that now in place of v minus 2, we have 4 minus 2v. And we did this because the differential of the denominator is 4 minus 2v times dv. So now you can just instantly write the integral. And on that side, of course, you have integral of this plus ln of mod c. You already know why we have chosen to write ln here, because ln will be present in these integrals, natural logarithm, and c is a non-zero arbitrary constant. So then, of course, you do the integration. This integral becomes minus 1 over 2 times ln of the absolute value of this. And on this side, you have ln of mod x plus ln of mod c. There was a mistake here. An equality sign was here. And then you go through the necessary steps. You do the calculation and cancel ln, and then you will have this. And do not forget to write y divided by x finally in place of v, because v is a variable that you introduced. So you have to go back to y. And the simplification of this, further simplification, I am leaving to you. Once you bring it to a respectable form, then you compare this solution, this family of solutions, with the previous one that we got by the other method.